I would also like to welcome you to the today's webinar. And the title of my presentation today is Challenges for Electronic Assemblies and Automotive Application. The presentation is structured as follows. I will start with a brief introduction of the System Reliability Assessment Working Group, which is a part of the Environment and Reliability Engineering Department. I will then briefly outline the main requirements of electronics in the automotive environment. Next, I will show you some typical failure modes, and then I come to a failure data analysis, where I have used an evaluation of data from the energy sector. In terms of environmental stresses, the conditions here are similar to those in the automotive sector. And I will briefly discuss the question sustainable versus reliability. At the end, I will summarize my presentation with a short conclusion. Some words to the Department Environmental and Reliability Engineering, short ERE, where I am a part from it. We combined the environmental and reliability point of views. Here we have two working groups which are deals with the topics recycling, eco-design and environment questions, and one working group which deals with the topics in the field of reliability assessments. Our mission is that we supported the development of sustainable and reliability electronic system using systematic assessments, and part of our work is the examination of aging phenomena on micro and nano scales, assessment of warpage issues and technology process issues, design for reliability on module and package level, combined load lifetime testing, accelerated test planning and development, system reliability and the mission profiles for this, and some approaches of condition monitoring for electronic systems. In our work, we use various methods along the development chain from the concept phase, design and reliability testing through to the application. In the concept phase, we support the risk analysis and planning with FMEA and MTBF or methods like this. In the design phase, we do simulation analysis and support the design with the analysis of necessary material dimensions, thermal and thermal-mechanical analysis, and also the impact of moisture. We support the test phase by developing test specifications and carrying out tests. And we developed and analyze mission profiles and developed condition monitoring strategies from an application perspective. Our experience, our expertise lies in the fields of process analysis, materials, the material characterization, the failure mechanism, and the system understanding. This allows us to support the design for reliability approach with three main aspects. At first, the system analysis and testing with root cause analysis, mission profiles, system level modeling, failure analysis, and stress tests and monitoring. The second aspect is the material characterization with characterization of mechanical, thermal-mechanical material parameters and the electrochemical testing. And additionally, with simulation approaches for early optimization aspects. For this, we have a lot of equipment which allows us to analyze different sample levels. These sample levels are materials and technologies, components, assemblies, and a little bit system, but or products, mostly yes, parts or system components. On this slide, I will show you a few very rough requirements of electronics in automotive applications. This list is not complete, however, it already shows a few major challenges. First of all, lifetime. In combustion engines, the parameters are 300,000 kilometers or 50 years or 8,000 hours. For the electrical vehicles, the first or the third and the second parameter are the same, but more than 130,000 hours is a requirement for the electronics which are located in the engine. Next, the fast development cycles are requirements. This means for a lifetime, which you want to test, 130,000 hours, a reduction in test times with the same lifetime protection and high robustness is necessary. For this, we need accelerated test planning, and the aim is a virtual release. Another requirement is you need compact and miniaturized electronics with a high current density, because the requirement is low weight with a high robustness. And this is the driving factor. All you need a low carbon footprint in production for electric vehicles. In the lifetime, we have a low carbon footprint. This means we need low material usage and the use of environmental friendly materials is necessary. If I had this in mind, and here for the example, typical failure areas in power electronic devices, as example, I will show you the typical failure locations on a symmetrical pictured power module. I have divided this into two paths, which may overlap under certain circumstances. First, in the electrical path, this can lead to loss of electrical contacts. This can be the result of crack in conductive layers, thermal-mechanical fatigue caused by CTE mismatch, electrochemical migration caused by moisture stress and corrosion, and electromigration caused by high current densities and higher temperatures. The red stars give you an idea where the failure could be located. And second, the thermal path, which you see here, this can lead to loss to thermal conductivity. This can be the result of the change in material parameters caused by aging of the materials or delamination of layers, respectively adhesion issues caused by mechanical stress, e.g. vibration. Typical power electronic failure modes in a package. Here I show you a few typical failure modes, which all fall under the term thermal-mechanical fatigue. We can have a crack in the die attach, heel crack, or cracks and bond interfaces, or delamination in the substrate, here for example a DCB. Further failure mechanisms are fatigue stress, intermetallic phase, electromigration, corrosion, whisker formation, which see you here, dendrites grow, and electrostatic discharge, thermal aging and oxidation of polymers, and delaminations. In the next slides, I will show you a few analyses of failure data. Here, the application was from the energy sector, more specifically photovoltaics and wind applications. However, as similar environmental pressure prevail here, the results regarding the driving forces that cause the failure can be transferred to the automotive sector to a certain extent. The main failed components are listed on the slides. On the left side, you see this for wind turbines, and on the right side for the photovoltaics. For the wind turbines, we see here phase modules, components like IGBT modules, driver boards, DC link capacitors, and bus bars. And the inverter control units are the main failure components. For photovoltaic systems, here string inverter, we see the semiconductor and electromechanical switches are the weakest links. For string inverter, a lot of PCB integration, also with a lot of PCB integration, PCB errors can be lead to power semiconductor defects, and in the most cases it is not possible to differentiate between driver PCB and semiconductor as a cause. If we take a look at the seasonal downtime of wind turbines, we see a cluster of phase module failures in the wet seasons, here in the summertime. This shows that humidity is a key driver of converter failures in wind turbines. Humidity, therefore, has a significant effect. You can see a slight regional difference between India and Scandinavia, here on the right. If you look at the downtime of photovoltaic systems, you can see that the failure occurrence, considering all failure categories, match with higher irradiation and ambient temperature and a high absolute humidity. If we then take a closer look at the course of the day, we see that the startup phase is particularly prone to failure in the morning hours. Here you see the the second highest number of the failures. Here we have mostly highest relative humidity in the morning hours because dew formation is possible. You also see a similar failure rate at noontime in the maximum power point. Here the temperature is the dominant key driver. Oh. Yes, and now let me come to the question or to the discussion sustainable versus reliability. The sustainable key aspects, the main aspect is low impact of the environment. These in both parts, in the production, it should be environmentally friendly. We have it has to be a low carbon footprint. We need or the requirement is the low material usage and the use of environmentally friendly materials. And recycling of these systems and the materials is a part of the production. It is on the end, but it should be a part of this. The operation side, a longer operation time is more sustainable. A high reliability and a high robustness is important for this. So we have a long life expectancies. So we can say life or reliability, lifetime is a part of this sustainability. Increase the operation time. Reliability means we increase the operation time. We can get it compact power electronic modules, increasing the robustness, and we get a high effort at the materials and higher costs. But we have a high number of different failure mechanisms in harsh environments. All failure mechanisms driven by humidity, temperature, and mechanical loads like vibration. So we have a high effort in the package. We have with this a lower possibility of repairability of individual components. We have a low possibility of recycling and lower reliability and recycling. We have a loss of material with regard of the circular economy. So we have to get in mind power electronics should be sustainable. But how much reliability is necessary to be really sustainable? Now let me come to my conclusion. The development of the right test produces and reproduce the domain error pattern from the various application areas is very important for the idea or for the requirement to have an sustainable system. For this, we need application-specific mission profiles, energies or energy system and automotive, a little bit or similar. We have multiple error images from the various field applications and of the system level, combined loads, temperature, humidity, vibration at the same time can change the dominant failure mechanism depending on the area of application. But at the end, we have to answer the question how much effort is required to achieve a high level of reliability in order to realize sustainable systems. High effort in the development phase at the materials, high costs, high carbon footprint in the production phase. This answer is at the end, or is to to bring it to this question is answered at the end. This brings me to the end of my talk. Many thanks for your attention, and I'm free for your questions.